Annenberg Media.
At first glance, there's nothing particularly remarkable about this scene. These are objects that you might find at any typical campsite. However, there is a connection between them that goes beyond their obvious function. Most of these items, as well as those that fill our everyday lives, are made, at least in part, of minerals, the natural materials of which the earth is composed. Geologists define minerals as solid substances that are naturally occurring and inorganic. Minerals also have a definite chemical composition in which the atoms are arranged in an orderly pattern called a crystalline structure. Thousands of different chemical compositions and crystalline structures occur in nature, and combinations of these result in thousands of different mineral varieties. If we were to take away the objects from this campsite around me that require minerals in their manufacture, there'd be very little left to look at or sit on. Human society depends on the products that it invents and manufactures, and minerals are an important raw material. The minerals we use in the manufacture of consumer goods, and that are a part of virtually any man-made object you can name, are also found here, in the rocks that make up the Earth's crust.
In this open-pit mine, for example, iron ore is extracted from the earth. It is smelted and combined with other mineral products to form steel, which is molded to make automobiles, ships, and skyscrapers. From these sand dunes, quartz grains are separated, then melted and molded to form glass, which is used to fill the windows of the world. Rocks are simply aggregates of mineral grains. Many granitic rocks, for example, contain mostly orthoclase, quartz, and plagioclase, while basalt typically contains plagioclase, pyroxene, and olivine. And so, apart from their value as components of everyday objects, minerals are also useful tools for classifying rocks. The minerals contained in rocks provide hidden clues about the conditions under which the rocks formed.
A mineral is like a little fossil. It's a historian of a past time. Fossils to us tell us about past living conditions of where that fossil grew and lived at a very different age. And minerals do the same thing. Like fossils, minerals in a given rock are millions, if not billions of years old. But they trap within themselves, within their own internal compositions, their own history. Different geologists use minerals in different ways. A geochronologist uses minerals to determine the age of a rock, whether it be in millions or billions of years, using the radioactive elements that are in each mineral. The sedimentary petrologist and stratigrapher use minerals in a sediment to determine how that sediment was formed into a sedimentary rock. And some of those minerals in a sediment tell that geologist about mountains that were once there eroded to form a sedimentary rock. The igneous petrologist and the metamorphic petrologist use minerals to determine the pressure and temperature recorded during a rock's crystallization from a molten magma or deformation during metamorphism. In plate tectonics, the structural geologist uses minerals as well. Many minerals record magnetic directions, and as the plates have migrated, the magnetic directions are shifted. And so minerals have recorded plate motion. So we have learned a lot about where the plates once were relative to today from the minerals. The different geologists have learned different things, but the minerals have recorded that information despite their great antiquity of age.
Over 2,000 varieties of minerals on Earth have been identified. And new ones are still being discovered. But most are rare, including some that have only been found at a single location on the planet. In fact, the common types of minerals number only about 200. Examples include quartz, olivine, orthoclase, and plagioclase. These common mineral varieties are called rock-forming minerals because they comprise most of the rocks on Earth and also serve as the basis for classifying them. Of course, before a rock can be classified, its minerals must be identified. This is one of the most fundamental tasks in all of geology. The differences between mineral varieties are related to their atomic structure. The atoms that make up a mineral are perfectly and symmetrically arranged in an almost infinite three-dimensional crystal latticework. This structure is held together by a variety of chemical bonds. Individual atoms often occur as electrically charged particles called ions. One important bond is formed when these ions combine to neutralize their charges. This results in the more stable configuration of a crystal structure. A somewhat analogous situation might be the relationship between loose cinder blocks and a cinder block wall that has been carefully constructed and mortared together. Both are composed of the same raw material, but the wall is strong and stable because of the way the individual blocks are mortared together. On an atomic level, each type of mineral has its own unique crystal framework based on an orderly arrangement of bonded atoms. Crystal growth occurs atom by atom, layer by layer, in exactly the same pattern, repeated over and over again. This regular internal structure has a great deal to do with the shape and physical properties of the resulting mineral. As it turns out, a mineral's physical properties are usually quite different from those of the elements that compose it. A good example is halite. Halite is a mineral that forms when sodium and chlorine atoms join during the evaporation of a lake. By themselves, each of these elements is extremely dangerous, sodium being an explosive metal, and chlorine a poisonous gas. Yet when they are joined together, sodium and chlorine combine to form something most of us use all the time: ordinary table salt. Another mineral with physical properties that are different from those of its chemical components is quartz.
And if you look at that mineral quartz, it's composed of silicon, which in its pure state is a silvery solid substance, and oxygen, which isn't a solid at all, but an important atmospheric gas that also behaves flammably. Silicon and oxygen are very different individually. They don't combine to form quartz under ordinary surface conditions, but inside the Earth, quartz-forming reactions are common. Quartz is harder than steel due to the three-dimensional bonding of its individual silicon and oxygen ions. It's usually transparent, forms beautiful crystals, very different from its pure, separated elements.
With a few simple tools, a steel knife, hydrochloric acid, a rock hammer, Geologists in the field can perform tests to identify minerals.
Each mineral has a distinctive set of physical properties based on its own unique combination of chemical composition and crystalline structure. Physical properties include the color of the mineral, the way it reflects light, the way in which the mineral breaks, and some simple chemical reactions. These are used to help identify the mineral. It's easy to see that this rock is made of different minerals because there are 4 different colors of mineral crystals. Color is a fundamental physical property of minerals. Look at this silver mineral called muscovite. It looks almost like a stack of paper with the individual sheets flaking apart quite easily. The tendency of minerals to break along flat planes is called cleavage, and cleavage is a property that's determined by the crystalline structure of the mineral. This pink mineral is feldspar. Unlike muscovite, it has cleavage, but there are 2 directions of cleavage at about 90 degrees to one another. The hardness of minerals is another identifying characteristic. Quartz is quite hard. It can't even be scratched by this steel hammer. Calcite looks similar to quartz, but is much softer and scratches easily. Like cleavage, hardness is a physical property that's determined by the crystalline structure of the mineral, and is a good way of differentiating between these 2 minerals. Another physical property of calcite is that it dissolves in dilute acid. Calcite is a carbonate mineral, and the acid releases the carbon as carbon dioxide gas. Quartz is a silicate mineral. It doesn't dissolve in acid, and so there's no obvious chemical reaction. The way in which minerals reflect light is the physical property called luster. Feldspar has a dull luster. It doesn't shine at all. But compare that to muscovite, which has a glassy luster. Metallic minerals, like galena, reflect light like a polished metal surface. Pyrite also has a metallic luster, but is a different color than galena. One useful way to distinguish between some metallic minerals is a physical property called streak. When we rub a mineral against a porcelain plate, we powder the mineral. And by comparing the color of the mineral in its powdered form to the coarse crystalline form, we can distinguish some types of minerals. Hematite is reddish-brown in its powdered form and gray metallic in its coarse crystalline form. Compare this to galena, which is gray, both in the powdered form and the coarse crystalline form. Geologists in the field use simple tests like these to help identify minerals in rocks. But this is only the first step. Some minerals are only present as microscopic crystals in rocks, others in only extremely small quantities. And some minerals can't be identified by physical properties alone. Petrologists, the geologists that study the composition and origin of different types of rocks, need to know much more about a rock sample like this and the minerals it contains. Once the sample is collected and identified in the field, it's taken back to the laboratory for a much more thorough analysis of the minerals.
Petrologist Lawford Anderson is analyzing a piece of granite from the Whipple Mountains, which lie along the Colorado River in southeastern California. The purpose of the investigation is to determine the age of the granite, as well as to figure out exactly where in the Earth's crust it originated.
That rock comes back to the laboratory, and we're going to learn to read that part of Earth history. We've got to open that rock up like opening up a book and start to read what kind of secrets are pent up in its mineralogic or elemental composition. One of the first things happened is that we saw that rock. And from that slab of rock that's removed, we have a piece of the rock here. And from the slab, we break it down to a smaller piece from which a very thin slice is made. That is a layer of rock that is sliced so thin that we can pass light through it in a microscope to look down and see how the different minerals are arranged, be they sedimentary, igneous, or metamorphic minerals. The nature of the way they're intergrown, their composition, tells us about the conditions of that rock's history, that part of Earth history.
In addition to microscope work, Anderson also uses X-ray analysis to provide important information about the composition of minerals and rocks.
We had that low one last week. Has that been corrected?
To prepare the sample for analysis, the rock is literally broken down. This is done by first crushing it into smaller and smaller pieces. Ultimately, the rock is pulverized to the consistency of a powder. The powder is carefully measured out. Then melted and pressed into the shape of a disc. Finally, the disc is subjected to X-ray bombardment that yields the precise composition of the rock, element by element. Another important analysis involves shooting beams of electrons at thin sections of rock to determine the individual mineral compositions within the rock. The data derived from these procedures is vital. It enables Anderson and his colleagues to ascertain the pressure and depth at which the granite formed.
What we found out about the rocks from the Whipple Mountains is that they originated from the middle crust of the Earth. Some 25 or perhaps even more than 30 kilometers down, those minerals were crystallizing from a magma that was in place in that level, deep in the Earth's crust, at their age of 89 million years. So today we've brought the rocks back. They're at the surface now, but they were once deep, and they record in their composition and in their mineralogy how the middle crust originates.
The conditions under which a mineral is created may be clearly reflected in its atomic structure, and therefore in its physical properties. Diamonds and graphite are perfect illustrations of the relationship between a mineral's environment of formation, crystal structure, and physical characteristics. Diamonds have long been coveted as perhaps the most beautiful and precious of all gems. Graphite, which is used in pencils, is extremely commonplace and far less valuable. Yet both minerals are made of the same substance, pure carbon. The great contrast between their physical properties can be attributed to the differing structural arrangements of their carbon atoms.
Diamond is the hardest of all minerals. Why is it so hard? It's because it has a very special, unique covalent bond that holds the different carbon atoms so tightly that they cannot be scratched. In contrast, graphite, also a carbon mineral, is held, the same carbon atoms are held with a very different kind of bond. And it's a very soft bond, and the mineral becomes soft, and that's why we can use graphite in pencils. So hardness is one aspect, and it's directly related to the bonding that holds the structure together.
The covalent bond gives a strongly interlocking atomic arrangement to the carbon atoms in diamond. The weak bonds of carbon and graphite, however, develop a layered crystal structure.
Graphite is formed under low-pressure conditions near surface, while diamond is formed under tremendously high pressures. In fact, needs great depths in the earth to form, depths that are well within the mantle.
It is these depths and pressures that give a diamond its covalent bonding and dazzling beauty, and make it the rare and sought-after jewel it has been throughout history. Another rare mineral with a long and illustrious past is gold. Few other minerals have ever had its economic or political power, yet unlike copper and silver, which have various industrial uses, gold has only limited practical value. The considerable value that gold does possess is based on its historical function as a kind of universal currency in a world where countries have little faith in each other's paper money. The power of gold is exemplified by the settlement of California. Until the middle of the 19th century, this was a wild, uncharted, sparsely populated region. Then came the discovery of gold at Sutter's Mill, and practically overnight, thousands of people from all walks of life pulled up stakes and converged on the area, hoping to strike it rich. The same kind of frenzied activity was then repeated at the end of the 19th century. Following a gold strike in the Klondike, 30,000 adventurers poured into what is now the Yukon Territory. Gold and other pure minerals are relatively uncommon. What makes them so rare is that unusual conditions are required for them to concentrate within the Earth's crust.
Metallic minerals, such as gold and silver and copper, all form the same way. They're precipitated from very hot water solutions called hydrothermal solutions that percolate up through cracks, up through fissures in the earth, and as they reach cooler regions, they begin to crystallize. And whatever metals and nonmetals that are dissolved in that hot water, precipitate out. In case of gold or silver or copper, it calls for very special waters, and that's why they're all very rare.
These waters are generally derived directly from crystallizing magma or from hot groundwater circulating through the rock overlying an igneous intrusion. Rocks containing economically viable concentrations of metallic minerals are called ore deposits, and hydrothermal ore deposits are among the more important sources of metal known.
Most of the elements that make up ores don't have a home in everyday minerals, don't fit into the structures of quartz or feldspar or mica. And as a lava or a magma begins to crystallize the common minerals, the elements are bunched up together and concentrated, being dislodged away from the growing crystals. Water is also building, and at some late stage in the crystallization of almost all magmas, water begins to boil off. And as it boils and rises out of the magma system, it takes with it all those elements that didn't have a home. And these go off and fill up fractures up through the rocks above the magma chamber. And as they reach the cooler rocks, they begin to precipitate.
Crystallization and precipitation from a hot solution is only one of several ways that minerals commonly form. A number of minerals crystallize directly from water. This occurs under certain conditions that favor chemical reactions between elements already present in the water. A common mineral that forms this way is hematite, sometimes called bloodstone by jewelers. Hematite usually forms in well-oxygenated water, where dissolved iron and oxygen react and precipitate around sand grains, eventually forming red sandstone. Evaporation of sea or lake water triggers precipitation of an important group of minerals called evaporites. Halite is an example. Other minerals precipitate directly from gases through a process known as sublimation.
The sublimation process usually happens when you have a very hot volcanic gas, like a sulfur dioxide, which can come out literally by tons per minute in a large volcanic eruption. When these gases start to cool, they'll go directly from the gaseous vapor state to individual crystals of sulfur and build a yellow mass around the volcanic vents.
Minerals also form by biologic processes, as when an oyster makes a pearl. In addition, sponges and corals make their shells out of calcium carbonate taken from seawater and precipitated as the minerals calcite or aragonite. As we've seen, minerals can form in many ways. Most are relatively uncommon, while a few dozen are quite plentiful. But no minerals on the planet are more abundant than the silicates. Silicates constitute more than 90% of all mineral varieties on planet Earth. Most silicates possess neither the political and financial power of gold nor the exquisite beauty of diamonds. But their economic value as construction material is enormous. And one of their common ingredients, the element silicon, is used extensively in a very specialized type of modern technology: computers. Pure solid silicon is crystalline and hard, so it can be sliced to a thickness of only a fraction of a centimeter. It's also a semiconductor, which means it can be made to conduct electricity. These properties make silicon the ideal raw material for the manufacture of microchips used in computers. These days, computer technology is so widespread that we tend to take it for granted. But without the thin silicon wafers made from common silicate minerals, the awesome processing power of the computer age might never have come about.
Minerals have played a fundamental role in the political, economic, and technological evolution of human civilization. Wars have been fought and empires created over the geographic distribution of precious metals, of gems, and industrial minerals. And today, mineral resources are more important than ever before. The primary concern of the petrologist, however, is purely scientific. Ultimately, the lure of studying minerals for these geologic detectives is to unravel the geologic history, not only of rocks, but of the Earth itself.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.